Hi guys, my name is IBM and today I'm going to solve 970221 October November 2022. This is AS level structured questions and without wasting time I would like to take you to the question paper. So here's the question paper. It's supposed to be 1 hour and 15 minutes. I hope I'll try my level best to keep time. I'll not read through the instructions. I'll not read through the data. You can always go through the data. You can always go through the formula. I'll go straight to the first question. The boxes in figure 1.1 contain terms on the left-hand side and examples of these terms on the right-hand side. Draw a line between each term on the left and the correct example on the right. So the first term is base quantity. A base quantity is the one which can be expressed in terms of base units. So a base quantity, when we look at, we say there are 7 base quantities: mass, length, time, talk about electric current, talk about temperature, amount of substance, luminous intensity. So the base quantity here is going to be electric current. Then base unit. The base quantities are expressed in terms of the units of base quantities are going to be base units. So there's only one unit. There are 2 units here. There's Coulomb and force, but Coulomb is a unit of charge, which is I times T. So Coulomb is ampere times second. So it's not a base unit on its own. So the base unit we have here is kilogram, which is the base unit for mass. Then derived unit, of course, the Coulomb is a unit for charge, which is current times time, and I've said this is ampere seconds. So the Coulomb is the derived unit. Then, of course, force is going to be a derived quantity. So force is a derived quantity. So a set of experimental measurements is described as precise and not accurate. Said what is meant by precise. So measurements are precise if they are very close to each other, giving a very small range between themselves. So it means the measurements have a small range. The measurements have a small range. If measurements have a small range, or we can say the measurements are close to each other. So if the range between the highest and lowest measurement is very small, then we say the measurements are precise. But then not accurate. For accuracy, if we have repeated measurements, for accuracy we always look at the average. So the average of the measurements should either be close to the true value if the measurements are accurate. If it is not close to the true value, then the measurements are not accurate. So they are saying not accurate. That means the average of the measurements is far from the true value. The average of the measurements. The average of the measurements is not close. Is not close to the true value. So the average of the measurements is not close to the true value. That is not accurate. If the average was close to the true value, then we would say the accurate. So the true value is that expected measurement. Let's say you are taking experiment to determine the acceleration due to gravity, and you know that the true value of acceleration due to gravity is 9.81. If you take repeated measurements and the average is very close to 9.81, then we say the measurements are accurate. Okay. An object, mass m, travels with a speed v in a circle of radius r. The force F acting on the object is given by this expression here. The percentage uncertainties of 3 of these quantities are given in the table. So we have F, M, and R. The value of V is determined from F, M, and R. Calculate the percentage uncertainty in V. So I'll first of all make V the subject from this formula here. So making V the subject, I think V is going to be the square root of F times R divided by M. That is making V the subject. So it's like, remember, square root is power half. So this is the same as F R over M raised to power a half. So because of the power, because of multiplication, because of division, I'll just sum up the percentage uncertainty. So I will say percentage uncertainty in V is going to be equal to a half into brackets. The power multiplies the fraction of percentage uncertainties. So this is going to be a half percentage in F plus percentage in R plus percentage in M. So when I substitute here, I have a half into percentage in F is 3 plus percentage in R is 5 plus percentage in M, which is 4. So this is giving me 12 over 2, which is 6%. So the answer here is going to be 6% or 6.0%. The value of V is 15 meters per second. Calculate the absolute uncertainty in V. So we change the percentage to absolute. So absolute in V is going to be, of course, 6 divided by 100, then times the value of V, which is 15.0. So I'll just check my calculator. 6 times 15 divided by 100, which is 0.9. So this gives us 0.9. Question 2. A steel ball is projected horizontally from the top of, so that means there is no initial velocity in the vertical, there's only initial velocity in the horizontal, from the top of a table as shown in the figure. The ball is projected horizontal at a speed of 4.9 meters per second. The ball lands on the ground a horizontal distance of 180 centimeters from the edge. So we have a horizontal distance and we also have a horizontal speed. So it means we can always consider the horizontal motion. Assume that air resistance is negligible. If air resistance is negligible, it means acceleration in the vertical is going to be g, but of course acceleration in the horizontal is always 0 because there's no force in the horizontal. Acceleration in the vertical is g because the weight acts vertical downwards. So calculate the time taken for the ball to reach the ground. So I'm going to consider horizontal motion. If I consider horizontal motion, I'm going to use S in the horizontal equals to initial velocity in the horizontal times t plus a half acceleration in the horizontal times t squared. When I put a subscript x, that means in the horizontal. So in the horizontal, we have 180 centimeters. I think 180 centimeters is 0.18 meters. So I'll say 0.18 meters equals to initial velocity in the horizontal is given as 4.9, then times t. Remember I said acceleration in the horizontal is 0 because there is no force acting in the horizontal. The only force acting is the weight, which is vertically downwards. So there's no acceleration in the horizontal. So this last part becomes 0. So this means t is going to be 0.18 divided by 4.9. Now check this, 0.18 divided by 4.9. So this gives me 0.0 I'll first check this, 180 divided by 100. This is 1.8, not 0.18. So this is 1.8. Sorry about that mathematical error. I'm not good at math, so 1.8 equals that. So this is 1.8. Okay, so I have to check this again. 1.8 divided by 4.9, that is 0.37. So I'll just write 0.37 seconds. Then calculate the vertical component of the velocity of the ball as it hits the ground. Vertical component. Of course, for vertical component, by all means, I must consider vertical motion. So I must consider vertical motion. So to consider vertical motion, remember initial velocity in the vertical, I'll quote u in the vertical was 0 because it was initially moving horizontally. So if I use v equals to u plus at, it means the vertical velocity is going to be the initial velocity action in the vertical. So the vertical velocity Vy is going to be equal to the acceleration due to gravity, which is 9.81, then times the time. Of course, the time is a scalar, so it is 0.37. So 9.81 times 0.37, that is 3.6. So the velocity here is going to be 3.6. Then determine the magnitude and the angle to the horizontal of the velocity of the ball as it hits the ground. Okay, so remember we have a velocity in the horizontal which was 4.9. Of course, it remains constant. If we consider the ball here, the horizontal velocity remains constant, 4.9, because there is no acceleration in the horizontal. But the vertical velocity, we have calculated this as 3.6, and the resultant is this one here. So we just use Pythagoras theorem to find the resultant. V resultant, it's the square root of the squares of all these ones here using Pythagoras theorem. So we have velocity of 3.6. So the resultant velocity is going to be the square root of 3.6 squared plus 4.9 squared. So we have root of 3.6 squared plus 4.9 squared, which gives us 6.1. So V resultant is 6.1 meters per second. So that is the magnitude. Then we have the angle. So if I want to find the angle to the horizontal, so I want this angle here. So if the horizontal is 4.9 and the vertical is 3.6, so I have the opposite and I have the adjacent. So that is tan. So I'll say tan of theta is 3.6 divided by 4.9. So theta is going to be the tan inverse of that, 3.6 divided by 4.9. Then, shift tan inverse of the answer. So this is giving me 36.3 degrees. So the magnitude of the velocity, we agreed that is 6.1 and the angle is 36.3. The ball is projected by means of a compressed spring which is attached to a fixed block as shown in the figure. Okay, so the ball is placed on a frictionless track. In front of the spring, the ball is then pulled back so that the spring has compression x naught. Okay, when the spring is released, the ball is projected horizontally as shown. Okay, so of course we have elastic potential energy when it is compressed, which is going to be converted into kinetic energy when the when the spring is released. The variation with compression x of the applied force F for the spring is shown here. Okay, I can first see what this is. The scale here is 2 divided by 10, which is 0.2, so this is going to be 6.4. The ball is a uniform sphere of steel diameter 0.016 meters and mass 0.017 kilograms. Calculate the density. So we know that density is mass divided by volume. And because it is a sphere, we know that the volume of a sphere is equal to 4 over 3 pi r cubed. So when I substitute for volume, the 3 goes up, so that the density becomes 3m divided by 4 pi r cubed. So I will just substitute 3 times the mass, which is 0.017, divided by 4 pi times, they gave us the diameter. You can just change this to radius. Radius is going to be 0.08. So times 0.08 cubed. So I'll check with my calculator. 3 times 0.17. Sorry, 3 times 0.017 divided by 4 pi times 0.08 cubed. So this is giving me a 7. Let me try to check this again. 3 times 0.017 divided by, I'll first say 4 pi. Divide by, I'll say 0.08 cubed. Why am I getting this? Okay, let me use my calculator well this time. Let me repeat. 3 times 0.017 divided by 4 pi divided by 0.08. Okay, so I'm getting 7.9 times 10 to the power of, I don't know why I don't trust this answer. Oh, I think there is a 0 missing here. I said my math is not good. I have to check this. 0.016 divided by 2. Okay, these are 2 zeros. Okay, there is a 0 missing here. Sorry about that. So there is a 0 missing here. So this is 0.008 cubed. I'll check this again. So that is times 4 pi. Sorry, 3 times 0.017 divided by 4 pi divided by 0.008 exponent 3 or power 3. Okay, I think this is correct. 7926.7. Of course, this can round off to 7900. Okay, 7900. All of the elastic potential energy in the spring is converted into kinetic energy of the ball. The speed of the ball as it leaves the spring is 4.9 meters per second. So they have said all the elastic potential energy becomes kinetic energy. And remember, kinetic energy is equal to a half mv squared. Show that the maximum elastic potential energy of the spring is that. So this should become equal to the elastic potential energy. So it means the elastic potential energy is going to be a half times the mass. What was the mass? I think it is 0.017. 0.017. Then the speed is 4.9, and this should be squared. So I'm saying the kinetic energy is got from elastic potential energy. So I'll just press my calculator here. 0.5 for half times 0.017 times 4.9 squared. Okay, this is 0.204. 0.204, which is approximately 0.20 as required. Well, this is in joules. Use the figure to determine the spring constant K of the spring. So to determine the spring constant K, it is a graph of F against what is X. X is compression. So the spring constant is going to be obtained from Hooke's law. From Hooke's law, F equals to Kx, which means K is equal to F over X, or this could be the gradient of that graph. So K is going to simply be the gradient. So on the vertical, I have 6.4 minus 0. On the X, I have 10 minus 0, but this is in centimeters. So I'll say this is going to be 6.4 minus 0 divided by 10 minus 0 times 10 to the power of minus 2. So 6.4 divided by 10 exponent minus 2. So this gives me 64. So the answer is 64 here. Use your answer in B Roman 3 and the values of energy given in B Roman 2 to determine the compression X naught of the spring. Remember, the elastic potential energy was equal to the kinetic energy. So the elastic potential energy, which is given by a half kx squared, should be equal to 0.20. That we have got it. We have showed that above. So we want to find the compression x naught. So I want to find x naught. So x naught is going to be 2 times 0.20 divided by k under the square root. So this will be the square root of 2 times 0.20 divided by 64. So 2 times 0.2 divided by the answer. Then I find the square root. So the square root is giving me 0.079. 0.079. Yeah, 0. So x naught is going to be 0.079. Depending on how you round off, you may get 0.080. The steel ball is replaced by a polystyrene ball of the same diameter but of much lower mass. It has a lower mass, much lower mass. The spring is given compression x naught and is then released. Air resistance on the ball is not negligible. That means air resistance is going to affect the motion of the ball after it leaves the spring. Explain why this ball leaves the spring with a greater speed than that of the steel ball. Remember, the mass is lower. So remember, the elastic potential energy is what is giving us the kinetic energy. And this is equal to a half mv squared. The elastic potential energy is a half kx naught squared, which is going to give us a half mv squared. But they said air resistance is not negligible. But still, you notice that x naught was the same, and you notice that v squared is inversely proportional to m. When you look at this part here, if all the rest are constants, v squared is inversely proportional to the mass. Remember, this was a lower mass, and v is actually inversely proportional to the square. I mean, the square of v is inversely proportional to m, or v is inversely proportional to the root of m. So if I find the square root of m, again, it will even be smaller. So the lower mass means a greater speed. Even if there is air resistance, still there will be a greater speed. So I'll say they have the same elastic potential energy. They have the same elastic potential energy. So that means they have the same initial kinetic energy. So same initial kinetic energy. Because initially the elastic potential energy is equal to the initial kinetic energy. But of course, later on, of course, V is inversely proportional to the square root. So they have the same elastic potential energy, so same initial kinetic energy, but a much lower mass means a greater speed, but much lower mass means a greater speed. Because remember, the speed will be inversely proportional to the mass. Okay. Why this ball takes a longer time to reach the ground than the steel ball? Of course, if we look at the ball falling, let's say it is just falling in air, it is going to be falling due to its weight. The force to air resistance is in the opposite direction. The resultant force is going to be W minus the force due to air resistance, and the resultant force is mass times acceleration, then equals to mg minus the force due to air resistance. Initially there was no air resistance, now there is air resistance. So air resistance reduces the resultant force on the ball, which means it reduces the acceleration on the ball. And also note that the mass has decreased. So a lower mass also means a smaller weight. So that means the average, if we consider the average component of the resultant force, the average vertical component of the resultant force is going to be smaller. And therefore, the acceleration is also going to be smaller in the vertical, which means it will take more time to reach the ground. So I'll simply say lower mass means less weight. A small mass would mean less weight. So less average vertical component. So we expect less average vertical component of the resultant force on the ball. And if there is a less resultant component, that also means there will be less acceleration in the vertical. So less average vertical acceleration. And if there's less vertical acceleration, it means it will take longer because the acceleration depends the time the object takes to cover a certain distance. So it takes longer. to reach. It takes longer to reach the ground. Then question number 2, define power. Of course, we know that power is work done over time taken. So I will simply say work done per unit time. And by the power is also energy transferred over time. So I can also say the rate of transfer of energy. This is work done per unit time, or the rate of transfer of energy. That is going to be power. I think I've spoiled this. So power is the work done per unit time, or the rate of transfer of energy. Mechanical power P can be calculated using the formula P equals to FV. Use the component of work and the definition of power. Use the concept of work and the definition of power to show how this formula is derived. Okay. So using the definition of the concept of work, we know work done is equal to force times displacement. S is standing for displacement. And we have seen power is equal to the work done divided by time, which means power is going to be equal to force times displacement divided by t. So power is going to be F, force times displacement over time. And we know that displacement over time is the velocity. And displacement divided by time is going to be the velocity, which therefore implies that power is going to be equal to force times velocity. The engine of a lorry provides 130 kilowatts of power to the lorry's wheel, the lorry's wheels when it is traveling at a constant speed of 25 meters per second along a straight horizontal road. Show that the resistive force opposing the forward motion of the lorry is 5,200 newtons. So we have the power, we have the speed, and we have already seen that power is equal to force times V. So the resistive force is going to be the power provided by the engine divided by the speed V. So this is going to be 130,000 divided by the speed V, which is 25. 130,000 divided by 25, that is 5,200 newtons. The lorry B travels up a straight section of road that is inclined at an angle theta to the horizontal as shown in the figure. The lorry has mass m and acceleration of free fall g. Determine an expression in terms of m, g, theta for the component of the weight of the lorry that acts parallel to the surface of the road. So we want a component that acts parallel. So remember, weight of this lorry is going to be acting perpendicular to this surface here, or vertically downwards, not perpendicular to the surface, but vertically downwards. So this is the weight mg, and we need remember this angle is theta. So if I try to resolve this perpendicular to the surface, this is perpendicular to the surface and also parallel to the surface. Of course, perpendicular to the surface, this angle here is going to be theta. So if I resolve perpendicular to the surface to be mg cos theta, which means parallel to the surface is going to be mg sine theta. Perpendicular to the surface is going to be mg cos theta, parallel to the surface is going to be mg sine theta, that is elsewhere. Okay, so determine an expression in terms of mg and theta for the component of the weight of the lorry that acts parallel to the surface of the road. So this is mg sine theta. So the component equals to m times g sine of theta. The total resistive force remains unchanged at 5,200 newtons, and the engine now provides greater power to maintain the speed of 25 meters per second. The total mass m of the lorry is 36,000 kilograms, and the angle theta is 1.4 degrees. So they say the resistive force has remained, so there's a force acting downwards, which is 5,200 newtons, and there's a component of the weight downwards, but the speed is remaining constant. So that means still the resultant force is going to remain zero. Resultant force should be zero. So we need to find the resultant force will be the total force downwards. The resultant force should be zero, so total forces downwards should be the same as total forces upwards. So the driving force of the engine should be the same as total force downwards. So FD for the engine should be equal to total forces downwards. So I will say driving force is going to be equal to mg sine theta downwards plus the friction 5,200 newtons downwards. That is going to be the total driving force, which is going to be the mass is 36,000 sine of 1.4 plus 5,200. That's total driving force downwards. Then the power is going to be the driving force is going to be Fd times V. I'm saying Fd upwards is the same as the total force downwards because the speed is remaining the same. The resultant force should be zero. So this is going to give me 36,000 sine of 1.4 plus 5,200, and I multiply this by 25. So 36,000 sine of 1.4 plus 5,200 times 25. Oh, I missed out. It was mg here. There's a g here. I think I'm very tired these days. So m is 36,000, g is 9.81, sine of 1.4 plus 5,200. Sorry about this. 36,000 times 9.81 sine of 1.4. Thirty-six thousand times 9.81 sine of 1.4 plus 5,200 times 25. So I'm getting 3.4546 times 10 to the power of 1, 2, 3, 4, 5, power 5. Okay, so that is 3.46 times 10 to the power of 5. They want the answer in kilowatts. This was watts. So in kilowatts, 3.46 times 10 to the power of 5 divided by 10 to the power of 3. So this becomes 346 kilowatts. So depending on how you round off, you may get 350 kilowatts. I hope I rounded off correctly. 346, yes. Polarization is a phenomenon associated with light waves but not sound waves. State the meaning of polarization. Of course, we know that polarization means confining vibrations of a wave in a single plane, which is normally perpendicular to the direction of propagation of the wave, of energy of the wave. So confining or making confining the oscillations or vibrations of a wave in a single plane. In a single plane which is perpendicular to the direction of propagation of the wave. So confining the oscillations of a wave in a single plane which is perpendicular to the direction of propagation of the wave, that is polarization. We make the vibrations, especially for the electric vector, to be just in one plane, that is polarization. Of course, we can't see polarization with sound waves because sound waves are longitudinal. The particles vibrate parallel to the direction of propagation of the wave. So state why light waves can be plane polarized, but sound waves cannot. So we know light waves are transverse and sound waves are longitudinal. Light waves are transverse. And sound waves are longitudinal. Okay, so longitudinal waves cannot be polarized. Two polarizing filters A and B are positioned so that their planes apart to each other and perpendicular to the central axis line XY, as shown. So we have here the vertical transmission. What is coming out of A is I naught. And you notice that this one has been rotated and its axis of transmission is horizontal. That means the intensity which comes out of this side is zero. Because if this is vertical and this is horizontal, it means it has been rotated through 90 degrees. So theta here is 90 degrees relative to the initial position. In other words, the axis of transmission is is perpendicular to the vertical transmission axis of the first filter. So theta is 90 degrees. So it means intensity which comes out of this filter B is going to be zero in that case. The transmission axis of filter A is vertical and the transmission axis of filter B is horizontal, so that they are 90 degrees to each other. Unpolarized light of a single frequency is directed along the line XY from a source positioned at X. The light emerging from filter A is vertically plane polarized and has intensity I naught. Filter B is rotated from its position about XY as shown in figure 4.1. After rotation, the intensity of the light emerging from filter B is a quarter of I naught. Okay, after rotation, the intensity is a quarter of I naught. Let's see which angle gives a quarter of I naught. Which angle of rotation? Calculate the angle of rotation of filter B from its starting position. Okay. So, first of all, we know that intensity is equal to I naught cos squared theta. And remember, I should be a quarter of I naught. So I'll say a quarter of I naught is going to be equal to I naught cos squared theta, which means cos squared theta is equal to a quarter, or when I find a square root, it means cos of theta is equal to a half. And of course, without even pressing the calculator, I think the cos inverse of a half is 60 degrees. But this is not the answer to this question. Initially, the instant intensity was 0 degrees. The question wants us to find the angle of rotation. the angle of rotation. So the angle to the vertical, which gives intensity of the angle to the vertical axis, which gives intensity of a quarter I naught, is 60 degrees. But remember, the plane was initially horizontal. That means the angle of rotation should be equal to 90 minus 60, which gives us 30 degrees. Alternatively, if you're a good mathematician, I want you to notice that if you consider the quadrant, if we have 60 degrees here, if 60 is in the first quadrant, cos is also positive. All science students take, all students take chemistry. So if we consider it in the first quadrant and this third quadrant, I think other angles which give a quarter when squared, I think this could be theta, could also be, is it 120 degrees? I can check. Cos of 120, but when I square this, it is positive, so 120 degrees. The other angle could be, I think, 240 degrees. I just keep doubling this. Then I could also have, okay, 60 plus 60 plus 60. When I add 60, it is going to be 300 degrees. All these angles will give cos squared theta to be a quarter. That means I could also have 120 minus 90. This gives me 30 degrees. I could also have, you could also have, no, this gives you 120 minus 90. This gives you, is it 30? Yeah, that is 30 degrees. You could also have 240 minus 240. I have to subtract 120. I also subtract, just a moment. So we said if the angle of rotation is 60 degrees, 60 is less than 90. So, I mean, if the angle theta was 60 degrees, so from its original position where the angle was 90, so that was 90 minus 60, which gives us 30. If we rotate through up to 120, so I'll say 120 minus 90, which is 30. If we rotate through 240, I would say 240 minus 90. I think this gives you 150. This gives you 150. If you rotate through 300, I think 300 gives us 300 minus 10, minus 90. This gives us 210. So the answers could be 30 degrees, it could be 150 degrees, it could be 210 degrees, and so on and so forth. So if you're a good mathematician, you can check all the other angles, because we want cos squared theta to be a quarter. And I think mathematically these are the angles which give you cos squared theta as a quarter. When theta is 120, 240, 300, and so on and so forth. You can continue checking the angles because you're a good mathematician. A microwave of intensity I naught and amplitude A naught meets another microwave of the same frequency and intensity a quarter I naught traveling in the opposite direction. Both microwaves are vertically plane polarized and superposed where they meet. Explain without calculation why these two waves cannot form a stationary wave with a zero amplitude. So one has intensity I naught, another one has intensity a quarter I naught. So, and remember, intensity is directly proportional to amplitude squared. So that means they don't have the same amplitude. They do not have the same amplitude. So the waves have different amplitudes. So we cannot have total destructive interference. So we don't expect zero amplitude or at the nodes. So we shall say waves have different amplitudes. So they cannot have complete destructive interference. So cannot have complete destructive interference, cannot have complete destructive interference, hence cannot have a resultant displacement that is always zero, cannot have resultant displacement that is always zero at nodes. So because the amplitudes are different, we can't have total cancellation. There is no total cancellation here. So that means we cannot have complete destructive interference. So we cannot have zero displacement at the nodes. Then determine in terms of A naught the maximum amplitude of the wave formed. Of course, remember I said intensity is directly proportional to amplitude squared. For the first one, its intensity was I naught, let it be K times amplitude A naught squared. Then for the second one, its intensity I should be equal to K times A squared. But remember, I is a quarter I naught, so we shall say a quarter of I naught should be equal to K times A squared. So I have this equation and this one here. So I can substitute the first equation into the second one, or I can just divide the two equations. But I'll make substitution. So it means a quarter. Where there is I naught, I'm putting K A naught squared should be equal to K A squared. So K has cancelled out. And that means A squared equals to 1 over 4 A naught squared. When I remove the square root, it means A, the new amplitude, is going to be 1 over 2 times A naught. But we want the maximum because the principle of superposition here applies. So the resultant amplitude, because they want the maximum amplitude. Resultant amplitude is the algebraic sum. So if it is maximum, we shall sum A naught for the first one plus a half A naught for the second one, which gives us, I think, 3 over 2 of A naught, which is 1.5. So the answer here is going to be 1.5. Then state Ohm's law. Of course, this is electricity. We know that current through a given conductor is directly proportional to the potential difference across the conductor, provided the temperature of the conductor remains constant. Current in or current through a conductor is directly proportional to the potential difference across the conductor, provided that temperature of the conductor remains constant. The variation of current I with potential difference V for a filament lamp is shown in the figure. So this is I against V for a filament lamp. The resistance of the filament lamp increases with the potential difference state, how the figure 5.1 shows this. Of course, we know that resistance for a filament lamp is going to be V over I. And if we try to check, I think let's check if V over I is increasing. Let me check a few values. I'll check a few simpler values. Let me check this one. So this is 3, the other one is 1. So the first, that is 3 divided by 1, which is 3 ohms. Let me check another one and see. Let me check at 8. That is 1.75, I think. 8 divided by 1.75. This is 4.6. So we see that the ratio V over I is increasing, which means the resistance is increasing. So the ratio of V divided by I increases as the PD increases. So our resistance increases. Then explain why the resistance varies in this. Of course, resistance increases because the temperature of the filament increases as the PD increases. So as the PD increases, for a filament specifically, the current also increases. And if these two increases, the temperature also increases. So the temperature increases. So for a filament lamp, basically the reason as why the resistance increases is because the temperature of the filament increases as the PD increases. The figure shows a circuit with a battery of EMF 12 volts connected to a linear potentiometer AB and two identical filament lamps P and Q. The battery has negligible internal resistance and lamps each have the same IV characteristic as shown in the figure. When the slider of the potentiometer is at its midpoint, as shown in the figure, the current I in the battery is 1.78 amperes. So we are saying the current here is 1.78 amperes when this is in the middle. Of course, when this is in the middle, the resistance of this part here is the same as the resistance of the other part here. That means the 12 volts is divided equally. So the PD across this first part is going to be 6 volts. The PD across the other part is also 6 volts. But note that this part here is in parallel with the P. So that means the PD across P is going to be 6 volts. So I'll write that V across P is going to be 6 volts in the first place. So I have to go to the graph and look for the current. 6 volts, I'll look for 6 volts from the graph. So the PD is 6 volts. So I'll look for this current here. This current here. So the scale is 0.05, so this is 1.55. So from the graph, 6 volts corresponds to 1.55 amperes. So the current in lamp P is 1.55 amperes. Okay. Then the total power dissipated in lamps P and Q. So remember, power could be I times V. Remember, they are in series. P and Q are in series, so the same current is going through them. So power is I times V. and of course the PD across them is going to be the same, because the PD across P is 6 volts. The PD across Q is also going to be 6 volts, because notice that this section is in parallel with the P, and the other section is also in parallel with the Q, so the PD is the same. So the power is going to be equal to 6.0 times 1.55, but because it will be power for P plus power for Q, so I'll just multiply this by 2. So this is going to be 6 times 1.55, then I multiply this by 2, and this gives me 18.6, which is approximately 19. So total power is 19. Alternatively, you can find the power from I squared times R. If I have the resistance, that would take me long, but if to find the resistance, this would take me more time because I don't have this. Or you could use V squared over R. So, but this is direct, I times the PD across, that is power. Then the resistance of the potentiometer between its ends A and B. So I have the current which goes to the resistors here. This is 1.55. So I now know the current here to be 1.78 minus 1.55. So the current in AB is going to be 1.78 minus 1.55. I think this is automatically 0.23 amperes. That is the current. Then the resistance AB is going to be the PD across AB over the current. Of course, the PD is the EMF, which is 12, and the current is 0.23. So 12 divided by 0.23, which is 52.2 ohms. The slider of the potentiometer in C is moved to end A. Of course, if it goes to end A, it means the PD across P goes to 0. If this goes to end A, it means the resistance for this side is 0. The other side is due to the length AB. So in that case, if the slider is at end A, the resistance is 0 this side, so the PD across that section is 0. So, and remember that PD is the same as the PD across P. So it means the PD across Q goes to 12 volts. So state and explain the effect on the brightness of lamps P and Q. So if it is moved to end A, we are reducing the PD across P. By the time we reach A, the PD across P goes to 0 because they're in parallel, they are directly proportional. So I'm saying the PD across lamp P decreases to 0 because the PD depends on the length of that part AB, or from the slider to A. If the length goes to 0, the PD across lamp P is 0 because they're in parallel. So lamp P goes off. So P goes out when the slider is at end A. Then of course, if the other one decreases, the other one increases. So PD across lamp Q increases to 12 volts. So this one gets brighter. So Q gets brighter. Okay, so Q gets brighter as the other one gets dimmer, and then it goes off, or it goes out. I think last is particle physics. A lepton is an example of a fundamental particle. What is a fundamental particle? Of course, a fundamental particle is a particle with no internal structure. So particle with no internal structure. particle with no internal structure, or you can say particle which cannot be broken down into anything smaller. Okay, then a lambda particle is a hadron that consists of up quark, a down quark, and a strange quark. Show that the charge of the lambda particle is zero. Of course, we know the charges. We know that charge of up is plus 2 over 3e. Charge of down is negative 1 over 3e. The charge of strange is also negative 1 over 3e. So total charge is going to be, remember it is up, down, strange. So it's positive 2 over 3e plus negative 1 over 3e plus negative 1 over 3e, which is going to be 0 over 3e, which is going to be 0. Then the lambda particle is unstable. It can decay into a neutron and a pion, as shown by that equation. The pi 0 particle consists of an up quark and an up antiquark. Compare the properties of an up quark and an up antiquark. So you have to compare up. This is a particle, and the other is an antiparticle. First of all, they have equal masses. They have equal mass. That's number one. Number two, they have equal magnitude of charge. Magnitude of charge, because up is plus 2 over 3e, and up antiquark is going to be minus 2 over 3e. So the magnitude is the same. Equal magnitude of charge. You must add the word magnitude. Equal magnitude of charge. Then but they have opposite signs of charge. Opposite signs of charge. One is positive, one is negative. Of course, you could also say they are both fundamental particles. Of course, you could also say up quark is matter, antiquark is antimatter. The quark is matter, and the antiquark is antimatter. One is a particle, another is considered to be an antiparticle. Explain why the neutron is classed a baryon. Of course, it is made up of 3 quarks. The pi 0 particle is classed as a meson because it is made up of a quark plus an antiquark. Okay, so neutron is a baryon because it consists of 3 quarks. Then pi 0 is a meson since it consists of 1 quark and an antiquark. 1 quark and 1 antiquark. Okay, I think that marks the end of paper 2.1. See you in paper 2.2. Until next time, bye bye.